Welcome to this webinar on electromagnetic source imaging on epilepsy recordings with Brainstorm. My name is Raimundo Casani. I'm a research software engineer at the Brainstorm team. This webinar has been made in collaboration with the Young Epilepsy section of the International League Against Epilepsy. First of all, Brainstorm is an app for the analysis of brain recordings of different modalities, and those include MEG, EEG, ECOG, deep electrodes, FNIRS, as well as multi-unit electrophysiology. Some of the characteristics of Brainstorm is that it's a free and open source application. It's based on MATLAB and Java, therefore it's independent of the operating system. It can run on Windows, Mac OS, and Linux. It's designed to be run in MATLAB. However, we also provide a standalone version in case the users don't have a MATLAB license. All the processing in Brainstorm is based on a graphic user interface where the main actions are click and drag and drop operations. Therefore, no programming experience is required. Brainstorm is a rolling release, and we have updates almost every day. And it supports most common file formats for recordings as well for anatomical data. Nowadays, there are more than 3,000 users that have been registered on our website to download Brainstorm. And because the best way of learning Brainstorm is through using it, we provide also online tutorials, with the introduction being a 30-hour self-training program. Besides, we have more advanced tutorials for specific cases. There is an active forum where all the requests and questions are addressed. And you can find us on different ways in Facebook, Twitter, and GitHub. And all Brainstorm work is possible due to the work of many collaborations in different institutions, investigators, engineers, graduate students all around the world. I would like to take this opportunity to thank all of you for the amazing work. And today's webinar is based on epileptic recordings that were published in Dumpelman 2011. And the paper Loretta allows reliable distributed source reconstruction based on subdural strip and grid recordings. The data is proprietary for the Epilepsy Center at the University Hospital of Freiburg, Germany, and its use and transfer outside of this Brainstorm tutorial is prohibited without the consent from their original authors. The description of the dataset, mostly the dataset was a card for a patient who suffered from focal epilepsy and focal sensory dyscognitive and secondary generalized seizures since the age of 8 years. The seizures were mostly at the sleep. And the data that was recorded was the anatomical data. It's a 3D MRI processed with free software. For functional data, we have EEG recordings during one night of sleep. 100 with the neurophile device. And the data was finally downsampled at 256 Hertz. The spike identification in the recordings were made manually by epileptologists at the Epilepsy Center of Freiburg. Just a disclaimer, not for clinical use, the performance characteristic of the methods and software implementation presented in this tutorial have not been certified as medical devices and should be used for research purposes only. Lastly, this webinar is based on the EEG and epilepsy Brainstorm tutorial, and I will put the link in the description. So let's start. First, we need to create a new protocol. So we go to File, New Protocol, we give it a name. We select a default anatomy no, and default channel file no, as we have the default anatomy and the channel positions for the subject. We create the protocol. Then we need, in the Brainstorm interface, all the buttons we can put our mouse over them. I will show a legend of what they do. In this case, we go to the anatomy view. We do right click over the main node and we create a new subject with the default options. Save. Now we need to import the anatomical data for this subject. So we do a right click over the subject and import anatomy folder auto. And the anatomy data was processed with FreeSurfer. We go to files of type FreeSurfer. Then we go to the anatomy folder in our sample epilepsy folder, anatomy, open. This will load the data was pre-processed with FreeSurfer and will compute the MRI normalization on all these surfaces. It can take a few minutes. Once the MRI at the surfaces have been imported, we can do right-click on them to display them and to explore. So in this case, we are going to display the head surface as well as the cortex. Right-click, display, just to verify that they look fine. And all right, so we just click in this X button to close all the figures and clean memory. Now we have our anatomical data imported in Brainstorm. Now what we need to do is to link the functional data. So we change to this second button that is for functional data. We have already here our subject that was created before. We do right click on it and then review raw data file. Here we're going to select the data folder over our sample epilepsy folder. And the data is in the format of the EEG delta MEG. So we just go with EEG delta MEG and we select the tutorial _ EEG.bin and we open it. Now this will import this will create a link to the raw data. It's important to know that it's a link, therefore our raw data is not modified. So first, let's just explore the channels that we have in the data with right click in the channel file. And we do edit channel file. Here we can see that 41 channels have been imported and some of them have already their type. For example, 26, 20, 25, 26 that are EOG, and 27 that is EMG, 28 that is ECG. However, these channels do not have localization. So we're going to close this. We're going to import also the localizations for the channels. We do right click, and then we go to add EEG positions from import file. The import file that we have in this data set is in the format of EEG and /ASA. So we just click tutorial electrode.elect. We open it. It's going to ask us if we want to apply a MRI transformation. We say no, because we're going to do the registration with MRI later. And now we say that it has been updated, the position for 28 channels, and not all of them were found. We click on OK. Now we just right click again in the right channel and we go to MRI registration to edit, to see how it looks. So these are the head surface and the electrodes. We click here on label just to see the names. But we can see there are some issues. For example, the electrodes are far from the head in some places. And in other places, the electrodes are inside the head. Like, for example, these before electrodes, or even the occipital electrodes. So the first thing we're going to do is we're going to use their positions of the head points positions to improve the registration. So we go to this button that is the redefine registration using head points. We click on it. It will ask us how many points we want to discard. So we just said 2% of points can be discarded in order to fit the position the best with the head. Just click OK. And it shows that the information of what happened. Just close this window. And now it looks better. The final step that we need to do is to project all our electrodes on the head surface. So we just click on the next button that is project electrodes on surface. now our electrodes look good. All of them are on the surface, and they have been registered with the head shape. So we just click on OK to save the things, and this has been the electrode localization. Now that we have done the co-registration for the electrode positions and the anatomy data, it's time to review the EEG traces. So first we go to the window layout, and we select tile. So all the plots are going to be automatically arranged. We then go to the right click on the link to the raw file, EEG and display time series. Here we can see that all the time series are over each other, so they are in a butterfly plot. We can change that one if we go to the display configuration button over here, and we change the mode to column, in which each channel will have its own raw. Now the default view for the y-axis is to have always the positive values on top, up. And in this, but for the review of EEG, sometimes we want the opposite. So this is the button that will do the flipping of the y-axis. So we just click and it will flip the y-axis. Now the negative values are on top and the positive are going down. This only affects the visualization and not our raw data. Another aspect that is very relevant for the analysis of epilepsy recordings is the time resolution. So let's just set to 5 now. And in this case, we're displaying 5 seconds of signal. However, with reviewing recordings for epilepsies, the common standard is to use 3 centimeters or 30 millimeters per second. And this can be adjusted in Brainstorm to match that resolution. So we go again to the display configuration on time and set access resolution. So the current resolution is 237 pixels per second, and we need to adjust this one to be 30 millimeters per second. However, the ratio between pixels and millimeters can change from the size of the monitor, of course, from different operative system, if there's some scaling done. So the best way to do it properly is actually to have 3 centimeters on the monitor is actually to use a rule to roll and measure. So in this case, I go and measure the distance between 1 and 2 in my monitor, and in this case is 43 millimeters. So we have our ratio that 237 pixels correspond to 43 millimeters. Applying that ratio, and if we want 30 millimeters, it will do doing the ratio, it will imply that we need a resolution of 165 pixels per second to display that. Just click OK. And now I just verified with my ruler that, in fact, that's the time resolution that I'm looking for. Now, other of the options that we can do on the display of the EEG traces is filtering. So we go to the filter tab in the Brainstorm, in the Brainstorm GUI, and we select the filters. So let's just add a high pass to 1 Hz and a low pass to 40 Hz. On our signal, well, we can just play with the high pass to see the effects. Same for the low pass. And important to note that these filters are only for visualization. They are not applied to our data. And another thing for the review of recordings is the montages. For now, we have only the data of the electrodes as they were recorded. However, we can change the reference. If we go to the record tab, then we have the electrodes. We say all. We can change to show the average reference to electrodes reference to the average. We just click average reference. and now it changed. This applies only for visualization, not on the data. And we can use different montages. Some of them that are more used in the some of them that are more used in the analysis of epilepsy recordings. For example, like the double banana, that is also known as longitudinal number 3. We just click on it, and now we this one is the one we are shown, where we have the difference between electrodes with the shape of the two bananas on the skull. And as well, we can review the same data with different the same EEG data with different visualizations. For example, to the disk, and with the sensor with a sensor cap. In order to, we can select different times of the signal, and we can see how we change the different visualizations. That's something very useful in Brainstorm, that because they represent the same data, they are linked. So updating one shows the other. On all the figures, we have always context menus where we can see, for example, in channels, we want to see the sensors, and we want to see in channels as well as their labels. Once we select a channel, this channel is selected in the other plots. Here we don't see it because we're seeing the double banana montage. However, we can change it to see, like, for example, all channels, and then we can select that our channels are linked. We can press the escape key to deselect everything. Now we close our figures. It was like the 3D version of the electrodes. We close it, and we can review as well the other signals that were recorded at the same time. For example, the ECG time series. And we can see as well the EEG time series. All right. In this case, because it's style, all the figures have the same size. However, we can change that. We can go again to the window layout option and select weighted. In this sense, it will assign more importance to the brain recordings, and in this case, EEG, on the figures. Here we can see that we have a very clear ECG trace, and from it we can detect the QRS complexes. This will be useful to detect false positives when we are identifying spikes in the EEG signal. So we go to artifacts, detect heartbeats. We select the channel name ECG, time window. We want to do it all the file, and for every QRS complex, we just want to call it a cardiac event. We just click run. And this creates, in our same record tab in the event part, now we have a cardiac group that has the times for all the QRS events. We can see in our plots that there's appeared these markers on the data. Those are the markers for the events. We just click on File and Save Modifications. And the EEG data was already analyzed by epileptologists at the Epilepsy Center in Fribourg. So what we want to do is to import the timing of the spikes that they found. So we go to File, and we go Add Events from File. The file type is array of times, and the file is the tutorial spikes. We just click Open, and we need a name for this new label. Let's just call it spikes. We click OK, and now it creates a new group with the spikes that were identified. In this case, there were 58, and we can click on the time of appearance to see the timing of these different spikes. And something like this case is not always we have the spikes already marked, so we can do the marking of the spikes in Brainstorm. So we go to events, we create a group that will contain our spikes. Let's call it like a fake spikes. And with having this group selected, we can jump to our recordings and press the letter E. This will create events on the places that we want. We can do as well with right-click and add or delete event. In this case, it's going to delete the event because it's in the time where we are. So it will create or delete events depending where we are in the recording. And yep, that's how we do the marking. Of course, we can change as shown before, we can change the montages to the one that is better for us to mark our spikes. For now, we're going to delete all this group of fake spikes. So we select the group, fake spikes, then events, delete group, delete events, yes. And finally, we just close our figures to save all the modifications. That was to add the spike markers. Close, save modification, yes. Now we want to perform some pre-processing in our signals. First, we need to check the quality. So we drag and drop the link to the raw file into this area on the bottom of the Brainstorm GUI, which is the one to use processes. So then we go on run. This open the pipeline editor. In this window, we can select the processes that we want to apply on our data. So we go to the button that is called Add Process. Then we select frequency and power spectrum density using the Welch method. We want to compute it over the whole file on window length of 10 seconds, 50% overlap, and we want to compute it only for EEG channels. We run it. This process will create a PSD file in our dataset. We can just double click it. And here, mostly what we are doing is the PSD in the log scale for all the different channels. If we want to see which channel it is, we can right click. And for example, see the sensor cap. At the same time, we do always like right click, channels, display sensors, right click, channels, display labels, and we can select them. We can select the different electrodes, and their PSD will be selected as well. So we close this. And something that we see is that the noise around 50 hertz that is expected for the power line noise is not higher than that component of 50 hertz is not higher than other components in the same range. Therefore, we are not going to use a notch filter in this recording. Just close figure. However, we're going to use a bandpass on the file. So again, we already have our file here, so we just click on run. What we want to compute is, first of all, we want to go to add process, reprocess. If we want to apply a notch filter, it will be here, but we won't do it in this occasion. So we want to bandpass filter, and we want to bandpass our EEG signals from 0.5 hertz to 80 hertz. And also, once they are filtered, we want to apply the average reference. So we go again to add process. Then we go to standardize and to re-reference EEG. As an option, we need to indicate which is going to be the reference. Here's the name of the channel. In this case, if we put the word average, is referenced to the to the average only for EEG sensors. And this is our pipeline that will run the two processes one after each other. So we just click on run. As we can see now, we have a new folder that is called Tutorial EEG Band, which is our signal that has been bandpass filter. And finally, what we want to do is to compute the PSD for this file. So we just put it in the process, and we run we run the process on frequency for compute the PSD. So frequency, power spectrum density, the same parameters than before, and we run it. So the only thing that remains is that we can plot the two PSDs to compare them. First, the PSD before pre-processing and the PSD after processing. We can notice mostly the most visual effect is the effect of them of the low pass filter at 80 Hertz. And we close our figures. After pre-processing, artifacts are still present in the EEG signals. Further processing is necessary. When working with EEG files, the independent component analysis, ICA, is the most popular approach to remove artifacts. In a nutshell, it decomposes the EEG signal in a linear combination of independent components, and components that are related to the artifacts are removed. Then the EEG signal is reconstructed using the remaining components. Therefore, the influence of the artifacts is reduced. Let's do this in Brainstorm. So first we need to open our bandpass filters EEG signal. Then we just select a duration of 10 seconds, starting from 520 seconds. That is where we know with their eye movement artifacts. We just change them, can change the gain with the plus and minus button. And how we know those are eye movement artifacts, we can plot alongside the EEG signal just to verify, and indeed they are. So now what we're going to do is to compute ICA. We go to the artifacts menu, then ICA components. We select a window that has eye movement artifacts. And then we just run it using the pcard method, which will find the independent components for this window. Here we have the operation that we're going to that are done performing our data. That is the EEG reference average that we did before, and the ICA decomposition. For now, we don't have any component to remove. So let's just plot the time series of the first two components. We select them and we click on display component time series. And those are the components. First, let's go just to turn off the auto scaling for the components and also for the EEG traces. Now we selected the components to remove, and we can see the effect on the EEG signals. So, yeah. So we select the first two components and we click on save. Then we just close all the figures to save our modifications. Now that we have performed the pre-processing and artifact removal, the next step is to extract EEG epochs around the spike events. To do that, we just go to our bandpass filter signal, we just right-click, and we do import to database. Here are the options. First of all, we want to import spikes from the whole recording. We don't want to split the epochs that we import. We want to use events to define those. So we're going to use around the spikes, and we're going to go from minus 300 milliseconds before the spike to 500 milliseconds after. We want to apply the ICA projectors that we found. And we don't want to remove the DC offset that has been already removed. And we click on create a separate folder for each type event. We just click on import. This will create a folder that is called spikes that has a spike epoch name. And if we open it, we can see that it has 58 files of spikes. We have imported our epochs around the spikes, so let's just start to explore their data. So we do right click over the group and we select displays as image and EEG. This plot is going to show us the activity for all the different spikes, all the different epochs. There are 58 as the number of spikes. And this is only for electro FP1. From the description of the dataset, we want to see the FC1 electrode. And indeed, we notice clearly the spike in that electrode. So what we want to do now is to plot the time series for that. Want to plot for that electrode. So we close our figure. We open first the figure for only one trial. And we go to this plus symbol in order to create a cluster that it's a set of electrodes. So we create plus, add cluster. We select the FC1 channel and we create a new cluster using that that channel. That's our cluster C1. We just rename it to FC1. Click OK. And we change in the option overlay to files because what we want to do is to plot this cluster for many files. So we just go right to the spike group and we select cluster time series. Now we need to save the modifications. Yes. What this plot creates is the FC1 electrode for all the trials. And now here what we can do is to plot it using the butterfly view. So we come back here to the display configuration, display mode, and butterfly. Here we can see an overlay of all the spikes that we have imported. So the next step, what we want to do is to compute the average of all these the average of all the spikes. So we close our figures. Now we clean our list in the process area. And we drag all the group. With that, we are dragging 58 files. So we go to run. We go to the process. We go to the process of average. We want to average files. What we want to do is to average everything using the arithmetic average. And we just click run. This will create a new time series that is the average of a spike. So we can double click it. And this is the average. We can see it in different ways. Let's just try by columns. And this data as well, we can represent it in other ways. We do right click, EEG, and displace in a 2D disk. Also, we can do right click, EEG, display as a 2D layout. Right click, EEG, and we can display it as well as 3D, like 3D electrodes. We can show again the labels with the Control E shortcut. And finally, what we can do is to move the different time using the arrows in our keyboard to see the evolution of our data in the scalp. Using this plot in the 2D sensors, as well, like all the traces in the respective place. It can shift to different times. And again, all these figures are linked. For example, when we select the FP1 channel, it will be marked in all the plots, and we can see at time 0, like that. This just click on escape, so it unselected. And we can see that this is the in time 0. This is the electrode with the most active. In this case, is with the negative amplitude. And we just close our figures. A brief note on source estimation. So what we are planning to do with source estimation is we want to go from the sensor space that will be our EEG sensors towards the source space that is the activity in the brain. It could be either on the cortex or in the full head volume, but that's what it's known as the inverse problem. In order to solve it, first we need to find the forward model, that the forward model also is known as a head model, and that takes into account the anatomy and as well as the source space. So we define a set of dipoles either on the cortex or the full head volume and the electrical characteristics of the head to understand how the activity in these sources is reflected in the sensor space. Once we have computed our head model, we can invert it, and we can invert it with some constraint that will be set by the different methods that are to solve the inverse model. And with that, we can obtain the sources the most probable sources that were the origin of the sensor's activity. Let's perform source estimation on the cortex in Brainstorm. First, we go to the anatomy view. We do right-click on the subject, and we go to MRI segmentation, and we generate surfaces using the boundary element method. We click on it. We use the Brainstorm, the implementation in Brainstorm. And for the number of vertices, in this case, we're going to select 1082 for the three of them. And we select the skull thickness of 4 millimeters. We click OK. And now our surfaces will be created. After this, we just need to be sure that our cortex is inside those surfaces to avoid any trouble while computing the head model. So we do right-click on the default cortex, that is the cortex 15,000 vertices. We do right-click, and we just click on force inside the skull. It will fix any vertex that is outside of the skull. In this case, 2 were found. So we just close those figures. And now there is this new cortex surface that is called cortex 15,000 vertices _ fix. And it's green, which means is selected as default. Now we go back to our functional data view. And our folder spikes, we do right-click, we compute the head model, we select the head model for the cortex surface for the EEG sensors, and we use the method open MEG. So we click OK. Then we are going to use the default values, and we are going just to run it. Just be aware of the requirements of memory. If this is more than in your system, you can go and use a smaller number for vertices for the different surfaces. Just click on OK, and this process may take some minutes, or between 5 and 15 minutes with these settings. Once the head model computation has finished, now we can see the head model file here. And beside that one, we need also to compute the noise coherence. In this case, we want to compute it from the recordings before importing, and from a specific section where we don't have spikes. So we do right-click on the preprocess continuous data. Then we go to noise covariance and compute from recordings. And we want to select the time between 110 seconds and 161 seconds. That is where we know there's no spike activity. So we click OK. It creates a new noise covariance file. We do right-click and copy to other folders. So now back on our spike folder, we do right-click over the head model and compute sources. we're going to use first of all, we're going to change the name because we're doing on the cortex, just to remind us. We're going to use the minimum norm imaging method using Loretta, the one that was used on the original paper. And using constrained sources that are normal to the cortex, sensor EEG, and we just compute. This will create a file that is actually a kernel in Brainstorm, which is a linear transformation that will go from the sensors to the source space. And we can see that in our average, now we have as well as a source. So let's just open those two files. We can open the spikes, and we can also open to display the cortical activation on cortex. We can always in Brainstorm do double click on the color bars to reset them. And now we're seeing the activity at the time of the spike. However, we can fine tune the plot of the brain. So we select it, we go to the surface tab, and we can change the values of how smooth we want to see our brain and the amplitude threshold for the values that are displayed. In this case, let's just settle with a smooth value of 50% and an amplitude threshold of 30%. So, yep. So here we can move our brain to see different views. We can even have them from right-click views. There are predefined views and their keyboard shortcut. Just stay with the top. And we can see the evolution of our spike again in the timing and just pressing the arrow keys. We can see the activity. And moreover, we can open our sources also in the MRI space. So we do right-click on the source. And we want to see cortical activations in the MRI viewer. Now our sources, they're going to be displayed over the MRI. We click on the MRI and we set our amplitude again to 30%. And we go to time 0. And this, we can play with the different cuts. We need to be sure they are in the displays that we are used to. In this case, they are in the neurological one. We can see that because left is over left and right is on the right part of the image is the over right, or we can change to the radiological, whichever you are more used to. And finally, we can find the specific maximum of the activity. We do right click and we go to views and find maximum. So this is the place that corresponds to the maximum activity. We can see the different coordinates in different coordinate systems. So let's just close all these figures. And now we want to compute also the sources, but in this case, using the full head volume for a source space. So we go back to our channel file. We do right click and we create a head model. Now we're going to use the MRI volume. And again, we're going to use the OpenMEG method. We click OK, the default parameters. And we click once more, OK. Now for the volume, we need to select because for the cortex, the grid of sources is actually the vertices of the surface. For volume, we need to define a grid. In this case, we're going to use a regular grid using the cortex with a resolution of 5 millimeters. And we just click OK. We start the process to compute the head models, and it will take as well something between 5 and 15 minutes. Now our head model for the full head volume is here. We can see it as it indicates that it's volume. And to create the its kernel to compute the sources with this model. We just do right-click, compute sources. And in similar case, we're going to use the minimum norm imaging method using the S-Loretta as measure. And we'll just add the volume indication. So to distinguish it, we compute sources. And now we can see there is a second kernel, and in our average file, there are two sources. What we can do is to open, let's open both. Right-click, cortical activations, and display on the MRI viewer. The same for the ones computing from the volume. And moreover, we can display as well the EEG traces. Now, with all this information, we can do right-click and views and find the maximum for the cortical, for sources on the cortex, and we find the maximum views, find maximum for the volume sources. We can just go to surface to see that it's the same amplitude for both. And we can, something that else we can appreciate is that the coordinates are very close to each other. Like the coordinates where it's find the maximum activity for the time of the spike. So the coordinates for the cortex head model and the coordinates for the volume head model. Finally, we'll just close these images. And it's worth to mention that there are other source spaces that can be, from which Brainstorm can compute sources that and methods like the dipole modeling and the dipole fitting. Those are available in Brainstorm, and the results using these data are presented in the online tutorial. As additional content, we can compute the time frequency representation of the spikes. So we select all the spikes in the space for processing, then run. Then we select the process frequency, time frequency, Morlet wavelets for EEG electrodes. And the Morlet wavelet options, we select the time definition, the same one as the input files, frequency definition, logarithmic from 2 to 80 hertz with the 40 steps. The default Morlet wavelet options, we want to compute power for each of the spikes, and the output, we want the average of all the time frequency maps. We click OK. Moreover, we want to normalize the time frequency map because it's scale, the power scales different at different frequencies. So we want to standardize the baseline normalization. We want to normalize from minus 200 milliseconds to minus 100. And we want to use the method, the event-related perturbation, which is event-related synchronization / event-related desynchronization. We select overwrite input files. We run it. So now we just plot them. We want to plot the EEG traces. We double-click the time frequency map. And we also display it in a 2D layout. So all the time frequency maps for all the spikes. In the plot in the middle, we can change the electrode that we're displaying. Let's just put the FC1. And here we can just see the difference in activity in time frequency with respect to the baseline. Just close our figures. While all the process that we did in Brainstorm was on the GUI, it's also possible to automate these actions through writing MATLAB scripts using all functions in Brainstorm. I hope you have find interesting this video, and we'll see you soon in the Brainstorm forum. Thanks for watching.